right? Because you don't want to be jumping out of the frying pan into the fire. So there are always things to consider. You don't want to take ridiculous risks in life, but there are some risks that we are willing to take because the benefits outweigh them. So it is with chemicals. So I want to leave you with a few points. I know that in some cases here I'm preaching to the choir, but the fact is that the members of the choir sometimes go out and sing to others. So if you need some weaponry to confront the diatribe that we so often hear against chemicals, here are a few points. Just because you find something doesn't mean that it's doing something, as is the case of the acetone or the formaldehyde in the apples. Whether or not a chemical is dangerous or toxic has nothing to do with its origin. Whether it was made by a chemist in a bush or by nature in by nature in a bush or a chemist in a lab is irrelevant. What matters is what that molecule is, what we know about it, how much we have studied it. The high-dose animal studies do not necessarily reflect what happens in humans. The human is not a giant rat, with some exceptions, obviously. But by and large, that's not the case. It's indicative because we can't do experiments with humans, but this is not the biblical standard. Why? Because even among closely related animals, there are dramatic differences. Dioxin, often talked about as the most toxic substance ever made by man, which may be true, never made on purpose, it's always a byproduct of an industrial process. It is the most toxic if you're a guinea pig. But if you're a hamster, you can frolic in the stuff. And these are very closely related species. If you look at aflatoxin, a natural substance found in mold, often grows on corn. Well, it's teratogenic, that is, it interferes with embryonic development in rats, but not in mice. So how do we know what it does in humans? Chocolate, we all love it. If it didn't exist, if it were a new product, just introduced, would have to be tested. Well, if we chose the dog as the testing animal, we would never have chocolate. But humans are different, right? We eat chocolate all the time because theobromine, the compound that causes the problems in dogs, is easily metabolized by humans. So the animal is not a perfect model. We cannot eliminate all risk. We have to be cognizant of that fact. Always has to be associated with the benefit, and we can never prove that something cannot have a risk. We can never prove a negative. Science can't do that. I couldn't even prove to you that reindeer can't fly. I don't think they can. You probably don't think they can. I couldn't prove it. We could take one, take it up to the top of this building and nudge it off. Let's face it, if that animal ever in its life were motivated to fly, that's the moment. We'd have a mess at the bottom. We could do it with another one and another one, similar results. What would we have proven? Those animals today, for some reason, could not or chose not to fly. Maybe there are some reindeer, maybe 8 of them. Given the right date, the right conditions, the right stimulation, maybe they can take off. I don't know. Science will always have opposing views, no matter what issue. But you know what? They will not be equal opposing views. The truth will always be closer to one side than the other, but you can always find an expert to back up any view that you have, even though it may be a minority view, but that doesn't get translated to the public by journalists who are trained to give both sides, usually giving both sides equal weight. The plural of anecdote is not data, and just because you repeat something many times does not make it true. And yet we see this all the time. No matter how many times you repeat that your neighbor was cured with a homeopathic medication of something, doesn't mean that homeopathy works. Homeopathy is chemical nonsense. Non-existent molecules cannot cure anything. It's impossible to predict consequences of all of our actions. Who could have ever predicted back in the 1930s when ammonia and hydrogen sulfide were the refrigerant gases used? Terrible. If you had an ammonia leak in your kitchen, bad. Replaced with Freon, wonderful. Who could have predicted that 50 years in the future, Freon would be found in the stratosphere, destroying the ozone layer? Impossible to predict. Today, though, we have a much better chance at predicting. Why? because we're gravitating towards green chemistry. We know a lot more about chemical reactions, about raw materials. There is less of a chance that we'll be encountering situations like Freon in the future. The fact is that the overall cancer rate today is basically stagnant. Contrary to what the activists say, there is no epidemic of cancer. Our life expectancy keeps going up. So indeed, we are doing some things right. And this particular year, International Year of Chemistry, gives us the chance to tell these stories about the reality of chemistry. It's not that we should be out there as cheerleaders for chemistry. That's not the point. It's not that all chemicals are good. Of course they're not all good. Not all chemists are good. That's not the point. The point is to give a realistic picture that chemicals are not to be feared or worshipped. They are to be understood. And to get the message out that basically every decision we make in life somehow involves making a chemical decision. And understanding molecules is extremely important, whether it's drugs, cosmetics, nutrition. We need education. We need it from the earliest levels on. We have to get across the message that the word chemical is not synonymous with toxin. And that, of course, the way we use the chemicals is what is critical. We cannot prove certainty. Of course, that's very elusive in science. The finish line keeps moving away from us. But the fact is that when we discover something new, we are not scared to change our mind. Contrary to many activist believers and the alternative medical practitioners who will use the same arguments that they've been using for 200 years. Nothing ever changes. Science is a self-correcting discipline. It doesn't mean that we have all of the answers to the puzzle. No, nobody has all of the answers to the puzzle. Puzzles are interesting things, aren't they? And sometimes they can be pretty confusing and difficult to solve, right? But if you get to know the right chemistry, sometimes, just like that, you can, in fact, solve it, right? So that's the basic message. I'm sure that there are questions that arise, but let me leave you with last thought. My old friend Joan Gusseau, who of course thinks that cows are smarter than chemists, and she goes around using that statement all the time in her public lectures because of course it gets a laugh. I would ask her that the next time she wants to know the nutritional composition of her food, she wants to know how drugs are synthesized and which are the good ones and which are the less good, which are the most appropriate plastics to use, which are the safest and the best cosmetics. Maybe she should go and ask a cow and see the kind of answer she gets. I suspect she won't be happy with the answer. I know because I've tried. And you don't get great answers. Of course, it doesn't mean that we as chemists always have the answer either. No, that's not true. There are some questions that will never be answered by anyone because they are just too complex. But I think with proper knowledge of chemistry, there are a good number of everyday life situations that we can talk about where we can give guidance. So I hope that I've been able to give you a little bit of insight into some of the problems that we face in the world of chemistry, and maybe given you a few tools to take along with you in case you ever get into arguments. And one last thing, because nobody ever wants to go home from any kind of a chemistry presentation without at least one explosion, right? And unfortunately, so often we as chemists are accused of creating explosions and chemical warfare, etc. I mean, truth is, of course, that's chemistry too. But let's just do one, why not? In my flask here, I have a little bit of water, about this much. That's all I have in there. And here I have some calcium carbide. Most of you probably are familiar with calcium carbide. Calcium carbide looks like little stones. Doesn't matter now, you don't need to see it. It reacts with water to form acetylene. And acetylene is highly combustible. So what I propose to do is to take my calcium carbide, throw it into the water, let it react, form some acetylene, and set fire to that acetylene. Like that. That was better aimed than I thought. We hit the ceiling, right? But what you want to really see is this thing embed in the ceiling. So let's load it up. I didn't wait very long, right? Let's let the pressure build up. Ready? 3, 2, 1. What do you know? In science, you have to expect the unexpected. Except that it isn't really unexpected. The first explosion used up all the oxygen in the bottle, so now the only place it can combust is where it comes into contact with oxygen of the air. So instead of an explosion, we have a lamp. Indeed, 100 years ago, that was the headlamp on automobiles. But we have something else. We have a point. And the point is that the same chemical that was used to create an explosion can be used to light our way through the darkness. That calcium carbide does not make any decision. We make the decision on how to use it. So the same chemical can be used to snuff out a life or to light our way through the darkness. That decision is ours. Let's get the message out there that chemistry is what allows us to make the right decision. That's the right chemistry.